Okay, let's look at a couple more examples. So this is example 5 from your text, and it shows the world population in billions for 8 selected years from 1950 through 2020. So you have the bar graph on the left, and then you have the scatter plot on the right. And again, that scatter plot tends to be mostly what we do when we're trying to graph just initial information to see if there's a pattern. We do like bar graphs too, but if we're looking for that relationship, if there's a pattern in the data, we typically do those scatter plots instead. So let's suggest two types of functions that would be good choices for modeling data. So if I look at my scatter point here, and again, you can pause the video and think about this at home. One thing I do notice is it does look like it's kind of in a straight line. It's not perfect, right? So remember that real world data is messy. It's never going to perfectly fit something, but you're looking for that kind of overall shape. So when I look at my scatter plot, one model that I'm thinking of would be a linear model. Okay, so that could be one thing that maybe I'm throwing around using this data point. Again, I can see it a little bit more clear with the scatter plot. Not all the points are on a line, but it kind of looks like there's a line with these middle points here, maybe a little bit of a linear trend. So maybe a linear model would work here. The other one that is suggested from your text is potentially an exponential model. And actually you can see that I think a little bit easier with the bar graph. It does look like it's not perfectly straight. It does look like there's a little bit of a curve here with increasing. And if you look at your values from 2.6 to 3.0, that's a change of 0.4. Then we're going from a change to 0.7. Then we're going from a change to 0.8. Then I have another change of 0.8. 0.8, 0.8, 0.6. So it's not quite linear. It seems like it kind of starts increasing slower and then starts increasing a bit faster. So maybe some sort of exponential model would work. So these are maybe the two that I would suggest here. Or also maybe a logistic model, which is a kind of exponential too, right? Where you have that flattening at the top. So those could be two potential ones. Now, what I want to point out as well is that this is not an easy process. It's quite involved. So a lot of times what we may do, if you see your data and you're not quite sure which model it may fit, so maybe you think you see a pattern, but there's a couple models that would fit there, then you may have to run the technology for both models. And we're going to see that in the next example. Okay. So here is that same data for world population, and we just have it written out in table format. And we're going to use our calculator to look at two different models. So here we went through and we used our TI-8384 calculator series, and we ran the regression models for linear, which is the one we thought that looked like, and also exponential. So here is the output. So again, I'm not worried about you running it on your own. I'm just kind of letting you see what the output would look like here. So this is your linear model. And then this is your exponential model, which were the two that we said exponential, that we were considering here to represent the data. So notice how in both cases, the R value is very close to 1. So see here how that R value is almost 1, is 0.9976. Here that R value is almost 1, 0.993. So actually this indicates a strong relationship between the data and either model. So I guess you could really use either model here to represent that data. It's only for 50 years. So if we expand our data set to more data, then I think that would change. But if we're just focusing on these 50 years, then actually both of these seem to be very good models to represent the data. This one is a bit stronger, right? 9976 and 9931. 9976 is closer to 1, but again, 0.99 is very, very strong in both cases. So both would really be good models. So let's use the figure to express each model in function notation, and we can round our numbers to 3 decimal places. So when you have that output here, let's do the linear one first. It gives you the general form up top. So it's telling you to use y equals ax plus b, and then it's giving you the a and the b value. So your a value here, rounding to 3 decimal places, is 0.074. And then our b value, 2.301. 1. So we're going to plug this in. A gets plugged in here. And then our B value. For the exponential, I see that the format is like this. It's A times B to the X. And again, we're being told that A is 2.634 and B is 1.016. So if I plug in those values to my formula, I have 2.634, and then that's going to be multiplied with 1.016 to the X power. So that would be our exponential model. And again, both of these seem pretty good. Your R value is almost 1 in either case, which indicates a strong model. So a strong correlation there. So let's answer the next part. How well do the functions model the world population in 2000? So let's focus on the year 2000 here. Now we started in 1950. Or 1949, excuse me. So 1950 was 1 year after, so 2000 is 51 years. So we're looking at a time here of 51 years that have passed. So X is going to be 51 in this case. And what I'm going to do is I'm going to plug this into both equations. So for my linear, I get that Y equals 0.074 times 51 plus 2.301. And I'm going to use my calculator. And let's see if I get there, about 6.1. And when I use my exponential model, again, my X value there is 51. Just be careful, make sure you do this first on your calculator. You want to do your exponent and then multiply it by that 2.634. And what you get here is about 5.9. So if I go up to my actual data, I can see that the actual data was 6.1 in 2000. So my better model here is right here. 6.1 matches, right? Again, we had to round it, but that's a very close match. 5.9 is still close, but this one is better. So our linear model would actually be better. So they are actually both very good models. Again, both of these values are very close to 6.1, and they also both have very high R values, very close to 1. So they're both good models, but this one's a little bit better, right? So it looks like the linear does a slightly better job of modeling that data. And you can see that at the R too, that R is just a little bit higher here. So that linear model is just a little bit more on track there with those data points. And like I mentioned, when trying to fit a model to data, the best way to start is to graph that data, see if you can recognize a pattern or patterns there. And then if necessary, use your graphing calculator to fit several models to the data. So here, there were kind of 2 models that we were thinking could be, and we used our calculator to figure out both models. Both ended up being very, very good, but it looks like that linear model is just a little bit better. So the best model is the one that yields the R value that is either closest to +1 or -1.